Welcome to the lectures on evolution of air interface towards 5G. So, in this journey so far, we have discussed various things of the 5th generation communication system, starting from the requirements, the evolution of different standards, and then we have talked about the different mechanisms by virtue of which the new requirements can be made. We have also talked about the various waveforms. Then we looked at the propagation characteristics, how the models are available, what kind of documents to refer to, and then we are looking at a very important class of techniques which would help in improving the spectral efficiency, which has been there and would also continue in the 5th generation or in general any broadband wireless communication systems wherever high spectral efficiency is requirement, and that is MIMO. We have talked about the diversity mode of communication, which helps in improving the bit error rate, and we have started looking into the capacity, which enhances the spectral efficiency in bits per second per hertz. So, we have discussed about one particular method in enhancing capacity by sending parallel data streams. So, we have identified that the MIMO signal systems, where there are MT number of transmit antennas and MR number of receive antennas, can open up R, which is the rank of the channel matrix, number of spatial CISO data pipes. So, one can imagine like parallel pipes going on, and each can communicate and each can have a capacity of a CISO link with a power proportional to the lambda, which is the eigenvalue of H Hermitian, or sigma squared, which is the singular value, the sigma is the singular value of the H matrix, that is the MIMO channel matrix. So, now let us get back to that particular discussion. So, what we said is that the situation when there is no preferred direction, that means when we do not have channel state information, then the best we can do is set the RSS, that is the covariance matrix of the transmit power, to IMT, and based on the expressions that we have discussed earlier, the capacity would be as given in this particular expression. And then we also saw that H Hermitian, which is a Hermitian matrix, can be expanded in terms of q lambda q Hermitian with the property that q Hermitian q is MR, and the expression simply translates to this. And using the determinant identities and the relationship of q, we find that further the expression can be written in this form. So, what we see is there is a lambda, which is the diagonal matrix. This is also a diagonal matrix, and hence this whole thing is a diagonal matrix, is what we have discussed, and determinant of a diagonal matrix would be the product of the diagonal terms, log product. So, log product of diagonal terms, this is what we had written. We had assumed let m be the number of links, or rather I equals 1 to r, and then what we got is, since there is a log, it can be expanded as summation of logs. So, this expression, if we look at it carefully, contains within it a CISO link capacity, and we are adding up this r number of CISO link capacity, and hence we had said it is a sum, it is adding up of the capacities of r CISO links, each with a power gain of lambda I. So, that is what we see, that the SNR over here is this, and ES by MT is by virtue of dividing the transmit power equally amongst MT number of transmit antennas. So, what we concluded was that this is the MIMO system which opens up R spatial pipes, and how to use this, if we have to see that, let us open up a new screen, and what we will find is that suppose you have a certain number of antennas at the transmitter, and there are a certain number of antennas at the receiver, and the H matrix lies in between. So, in that case, if we are sending signal S1, S2 up to SR, let us say, or SM for simplicity, when it goes through the channel, the signal that is received in each of the antennas are Y, you could write it as MR or MT in this case. So, we would write Y is equal to H, which is the H matrix, times S plus noise, right. So, now what we see is that this is a MR cross empty matrix, or you can for sake of simplicity let us take it as M. For the non-square matrix, of course, you have to do the pseudo inverse, and this is M cross 1, and this is also M cross 1, this is also M cross 1. So, let us say both the sides have M. So, now what we are effectively doing is sending different signals. Now, if we compare this with the earlier mechanism of STBC, we had sent S1 and S2, and again we had sent in 2 time intervals T1 and T2. Whereas, here in the same time interval T1, you are sending different symbols, each of this SI element of the constellation point. So, each of them can be selected from the complex constellation, right. So, that means each one would be a complex value x I plus j y I, indicating one of these values, and they will be going out. Channel, as we have already said, it will be again complex values, noise is also same. So, now in order to recover S cap, you can use various different mechanisms. So, we would say H equalizer times y, and one of the simplest equalizers in this case would be H inverse if it is a square matrix, otherwise it would be the pseudo inverse, right, which would take us through that. So, if we execute this expression, what we get is that H inverse H S plus n, since we have taken square and assumed it to be invertible, we would get it as S plus n, this vector. So, that means each of the elements that we receive are the transmitted element plus the noise element, right. So, we must remember that each y I is sum over H, if this is 1 H 1 k, let us say H 1 k, k equals to 1 to m t, but I am writing m over here, S k plus noise 1, and then you could simply generalize it by writing y I is equal to H I k. So, that means each of the received signal I equals to 1 to up to m r, but I am writing it as m. So, that means each contains inter-symbol interference, as you can clearly see, but if this channel is invertible, then we would be able to recover everything and there is no ISI, and this kind of mechanism is kind of zero forcing, where we are forcing the interference to 0 and getting a coefficient of 1 against the desired signal. Instead of using H inverse, one can use H pseudo inverse. We have also said H EQ could be also based on MMSE criteria, or otherwise one can go for advanced non-linear processing also at the receiver end. But the scheme is very famous because of its simplicity, and this is usually known as the V blast or the vertical blast. Blast, the name coming from Bell Labs layered space time communication system. So, this is the very simple system of communicating, where we send parallel data streams or parallel symbols which go through this channel, and they can be recovered depending upon the channel characteristics, right. So, this is what matches with the definition of whatever we have discussed over here, right. So, let us see that. Okay. Yeah. So, we have discussed about a very common method of transmitting and sending in parallel data pipes while channel is not known at the transmitter. So, then we move further to the situation where channel may be known at the transmitter. So, that is CSI is available at the Tx. We have already explained how CSI can be made available at the CS at the transmitter. So, there could be various methods. Just to summarize, one could be in time division duplexing mode assuming channel reciprocity. And in FDD mode, that means frequency division duplexing, it could be through feedback. Now, these all sound good, but this sounds to be very easy and very nice way of doing it, but we must remember that we are talking about point to point link. So, in case of point to multi-point or multi-point to point or multi-point to multi-point, there is the notion of interference, which is not reciprocal in both the directions. Okay. So, in case of interference, it may not be reciprocal in both the directions, and hence we may not be able to exploit this kind of thing, and there this explicit feedback is very important. Explicit feedback means you have to give a feedback, although there is a term called explicit feedback which is used in different ways. So, here we assume that CSI is available at the Tx, okay, either through feedback or the principle of reciprocity, and this is what we do over here. So, the channel, we have seen this mode of analysis earlier when we said the dominant eigen mode. This H can be decomposed into its singular value decomposition as we have over here U sigma V Hermitian. So, sigma contains the eigen values, sorry, the singular values, okay, and U and V are unitary matrices which contains the vectors corresponding to these singular values. Okay. So, now if you look at the received signal is H times S, but at the transmitter we do some pre-coding. As you can see, there is this V vector, that is the pre-coding. Okay. So, S is the signal, V times S produces the S which we had been using in our earlier notation, and this kind of precoding can be called as SVD based precoding. Okay. And similarly, at the receiver, what you see is that this is corresponding to HEQ in the previous discussion that we had. So, now if we concentrate on the set of equations, we have U Hermitian from this we are getting U Hermitian multiplied by, if you look at H get expanded as U sigma V Hermitian, and V is the precoding at the transmitter plus U Hermitian noise because of receiver processing. So, now what you see is that U Hermitian U is identity, V Hermitian V is an identity. We are left with sigma times S. So, that is what you get over here, sigma times S. So, sigma times S, sigma is a diagonal matrix as we have stated over here, right. So, we have sigma 1, sigma 2 and so on, and S is what we have S 1, S 2, so on. So, effectively what it means, and of course, this is Y. So, Y 1, Y 2 and so on. So, if we break down the elemental equations, we will find Y I is equal to, of course, this is the scaling because of the energy normalization, times we have stated earlier that lambda I is equal to sigma squared I, where lambda I are the eigenvalues of H Hermitian and sigma belongs to H, the singular values of H. So, from instead of writing sigma, we will write it as square root of lambda times Si plus Ni tilde. Ni is the noise for that particular received signal path. So, now what you see is that the received signal can again be broken down into R number of spatial data pipes once again, and hence in a similar manner you would be able to get the capacity expression as we had discussed earlier is a sum. So, we are getting the sum operation over here of log, because we had log determinant, inside the log we are getting a diagonal, because look at this, this is a diagonal, this is causing the diagonal matrix. Okay. There was I MR that would have been there. So, now the expression is ES because of this, because it is taking SNR expression, the square root has gone, N naught because of the noise part, okay. And we are saying lambda I, there was square root. So, now it is lambda I, but we have included gamma I as the new entry into the system. If you compare this expression with the earlier expression we had used RSS is equal to identity matrix, but here since CSI is available at the transmitter, we have the option of accessing the modes. Modes means the spatial modes. Okay. So, we are able to access the spatial modes, but in order to access the spatial modes, this is the power control or power sharing you can say for each of the mode. So, this is one of the resources which are being used, and what we see is that here it is mentioned gamma I is E of expected value of the sigma power of the power in the ith branch. So, now what you will find is that RSS which was set as I earlier, this is not what we will use in this particular case. Earlier we had used because CSI was not available at the transmitter. So, now what we will get back to is RSS would be the diagonal matrix which will contain these elements, which is E of S I squared, like that these entries will happen. So, that means RSS, if we recall the expressions that we had discussed earlier, we said that you maximize over the choice of RSS subject to this constraint. When CSI is not here or not available, we had set RSS to identity, but now CSI is available. So, there is a particular choice of RSS which can be determined, which can be used. So, RSS is basically the covariance of the received signal. So, this is here, and of course, the signals are independent, hence these elements would be 0, but I mean we are getting diagonal values which are the powers of each of the paths. So, what we have as the capacity expression finally is the maximum value of this such that this constraint is held true. So, we are left with finding the power distribution within the powers constraint, that is what is the problem. So, this in this expression we have just simply put it power control, but still the values of these have to be found out. So, that is the next stage of operation while implementing this. So, just a statement before we move forward, these kind of mechanism are called SVD based precoding, and as you can see in the diagram, the S signal is multiplied with the V vector. So, basically when you write down, you are writing S multiplied by V, and then it is going to the channel where it is getting multiplied by H, and then at the receiver you are multiplying by U Hermitian, and then what you are getting is S tilde cap, correct. So, that is what we are having, and this is what is given over here. Each of the data pipes have this kind of amplitude or power, and we are left with the amount of power that we dedicate to each of these links. Okay. So, the gamma I optimal can be found in this manner, where this plus sign indicates positive values. That means, if x is greater than 0, if this argument is greater than 0, then you take the value. If it is less than 0, then you just apply 0 over there, and this is for all the R streams, because we have R data pipes, okay, and of course, this constraint is maintained. So, we are not going through the details of how to find this out. This is available in the reference material. So, the optimal energy allocation is found through iterative water pouring. Okay. So, we will just explain what it means. So, what you do is that you set p to 1 through iterations and you calculate this expression. Once you have calculated these expressions, then you can feed this mu into this expression, which is derived from the expression above. Okay. So, now we would go through these iterations and you can find out gamma I. In case the solution is less than 0, you are not going to use it. If it is only positive, then you are going to keep it. So, that is what it says. If this value is less than 0, discard this channel, put this equal to 0, rerun the algorithm, p incremented by 1. So, you get slowly the non-negative values or the values which are greater than 0 as your remaining streams. So, let us see how does it look like. So, if you look at the expression, we have a mu take away something. So, mu is a constant term. So, we have the mu threshold across the different spatial modes, okay, and each of the spatial mode has empty n naught by E s upon lambda. So, if we look at that particular term, empty n naught by E s lambda I. So, this you can easily write it as 1 upon E s by empty n naught times lambda I. So, now carefully look at the expression here. This expression is the channel strength. If we go back and see this expression here, or if we go back and see the expression there, that means, if we see this expression, we said it is the channel strength, that is what we have mentioned in this particular statement there. So, what we see is that we are taking away this entity from mu. So, let us write mu over here, mu minus this. So, inverse of the SNR. So, inverse of the SNR for that particular link. Okay. Inverse of the SNR, what is the meaning of inverse of SNR? So, what we mean over here, that if gamma if lambda I is very large, then this value is small, right. So, that means you give the power which is as close to mu as possible. If lambda is small, that means when channel power is small, then this entire thing is very large. If this number is very large, this entire expression is very small, that means the power you are allocating is very small. In other words, if lambda I is high, you allocate gamma I which is high. If lambda I is small, then you allocate gamma I which is small, and this is the famous water pouring algorithm. So, what we see is that this quantity indicates the noise. So, larger the channel strength, lesser is the noise, more is the power to be allocated. So, with respect to some threshold, that is what we have set as mu, the amount of power that you are going to fill in is proportional to the channel strength, right. So, after you do everything, only all the total amount of power that is going into the channel or the signal to noise ratio or the total amount of power, they maintain the same value which is mu, and whatever is in the denominator term is a significance of the amount of noise. Now, if the channel is weak, very weak, like these channels, then you are going to get a negative value in this expression. If it is a negative value, you do not use that channel. That means, the channel is too weak to be used. So, this is another level of mechanism that has to be added onto this. So, now if we get back, so we have got the gamma I values, this is gamma 1, gamma 2 to gamma r. So, this is fine, you can calculate the capacity, but in both the schemes, that means, whenever you are doing, either you go for blast or you go for SVD precoding. So, in this case you use an identity matrix, here you use RSS. RSS is determined through gamma I opt through the algorithm we have described, and now what we see is that in each of the cases, in both these solutions we had only talked about the power. Now, once the power is known, then the data rate also has to be decided for practical communication systems. That means, the set of constellation that you are going to choose has to be decided. That means, depending upon the SNR, whether you are going to use a QPSK or whether you are going to use a 16 QAM or whether you are going to use a 64 QAM, that depends upon the signal to noise ratio of the particular link. So, what we mean to say is that depending upon the particular link's SNR, which is determined by the earlier expression, you can choose different constellation for different streams. So, this is called per stream rate control. Right. Okay. So, you have got per stream rate control, and together you can achieve high spectral efficiency. Now, one important thing I would like to mention over here is that in SVD based precoding, if we go back, what we find is that there is this precoding matrix V which we are talking about. So, if we look at this precoding matrix V, you have S vector, which is nothing but S1, S2 up to SR, that means R data sets. Each, so we select R number of columns over here. So, basically V11, V12, let us say V1 MT, like that V1R up to V1, sorry, this should be V21, this should be VM1 and this should be VMR. So, we select R such columns. So, this is the precoding matrix, and this is dependent on channel state information. So, this is absolutely dependent on channel state information. So, if we have channel state information, the precoding matrix weights are decided based on the H. So, if H is known at the transmitter, then only we can achieve this scheme, and if H is not known, one can go for blast. Now, these two mechanisms are extreme ends. On one end, we do not have any information at the transmitter, the other end we have full information at the transmitter. But now, what we see is that something else can also be done. Okay. So, let us see what can be done. Okay. What can be done is we have the transmitting antennas, we have the receiving antennas, right, and what is happening is H is a matrix. So, we have the symbols S1, S2 up to a certain number, let us say L, and then they are getting processed through the precoder. So, we have selected in the previous case the columns from the V matrix which are generated from the H matrix. Okay. So, this means there is perfect match with the channel coefficients, because at the receiver you are again using a linear processing, that means you are using post processing is the post processing matrix, where you are taking u1 vector, u2 vector, of course, you have the Hermitian up to ur vector, let us say. Okay. So, now the number of entries or number of elements is equal to the number of antennas, whereas the number of data streams is less than or equal to the rank of the channel. So, we have this S vector, we have that goes into the precoder, which goes to the antennas. This is what we had drawn, which goes through the channel, and what we mentioned is these columns contain entries which are of empty length, that means, if there are empty number of transmit antennas, and S has SL number of symbols, where S is less than or equal to empty, which you can put as less than or equal to MR, and then everything would hold out. So, now this we have said depends entirely on the channel. The other case is extreme, where there is no preference. Now, the question is, can we do something better? I mean, why something better? Because the amount of feedback is very high in this case, is extremely high. So, now what people have thought of, or intelligent ways of doing thing, is that we could have various pre-code books designed, that means, we would call them as code books, which would contain complex weights, and there could be various such matrices. Okay. And if we have, let us say, capital N number of such matrices, we would require log of n with a base of 2 number of bits to be used in identifying what operation is to be done at the receiver, and these are not dependent on the channel, these are predefined, right. So, what the receiver does based on H. So, if we say that the received signal can be written as S vector with some precoder matrix W, then it goes through the channel, and then there is noise. So, the receiver can think of doing a processing in this manner, and the receiver needs to find out the index of this matrices, which would maximize the SNR or maximize the capacity or would minimize the BER, depending upon the requirement. Now, once the index of this W matrix is identified, because the transmitter and receiver both knows these matrices, the receiver has to feed back only the index of W matrix, that means, which matrix is to be used. The transmitter would use that matrix at the transmitter, the receiver would use a corresponding matrix at the receiver. A very general thing would be, there would be a pair of matrices W and W tilde, we can say that, right, and one could use in either way. So, effectively, in the previous case, when we were doing SVD, in the SVD case, you are sending back H matrix. Now, if it is, let us say, 16 cross 16, that means, there are 256 elements, right. So, there are 256 elements, each element would contain 2 entries because of complex. So, that means, you have 512 real entries, and if you would send at even 10 bits, you would have 5120, that means, nearly 5 kilobits of information to be fed back for processing. Whereas, if you compare with the scheme over here, if I have n number of such precoding matrix, I just have to use log n base 2. So, even if I have, let us say, 250, if I have 256, let us say, then this is equal to 2 to the power of 8. Okay. So, if it is 2 to the power of 8, yeah. So, then I will require only 8 bits of information. Okay. So, that means, I require only 8 bits of feedback over here compared to the huge amount of feedback over there. So, of course, with the reduced feedback, the quality of SNR and the channel capacity would be significantly reduced, but this is one important strategy which is necessary to realize large scale communication systems. Okay. So, with this, let us move on to see some of the code books that are used in LTE, and similar things are extended in the newer generation. So, I will just show you a few sample of such code books that are used. So, let us look at this particular slide, which talks about code book index, number of layers. That means, if there is only one layer meaning that one layer means, sorry, let us take the right pen. One layer means that you have only one spatial pipe, right. So, sorry, this is the number of layers. So, that means it is the number of spatial pipes. So, that means L, what we have indicated earlier, is basically the number of layers. So, although we can have a large number of antennas, we may choose to use only one data pipe. So, when we choose to use only one data pipe, what do we do? The precoder should contain only one vector, and there would be only one signal over here. So, this signal gets multiplied by all the elements of this vector, and then they go through the transmitter. Similarly, you have a vector processing at the receiver, and you extract the signal at the receiver. This particular case is similar to the dominant eigen mode, but there this vector is chosen from the channel's SVD. But here we are saying that you can have different channel vectors. So, these are the different channel vectors. So, if we had to send back a channel vector, we would require at least 2 elements to be fed back, and I mean the number of complex bits would be significantly large compared to the option that we have over here. So, since you are choosing between only 4, you require only 2 bits of information to be fed back. Okay. If you are sending 2 layers, this particular example has a code book defined over there. So, if I am using code book index 0 or 3, we are actually not using any code book. So, one can think of an identity matrix, whereas if you are using code book value of 1 or 2, you are choosing this or this matrix respectively, right. So, if we move further, what we find is that this contains the different code books that are available. So, number of layers is denoted as M. So, it could be 1 layer, 2 layer, 3 layer or 4 layer, and then there is a particular mechanism of generating these matrices through these UI vectors, and then all one has to choose is which particular matrix one is sending. So, out of 16 possible options, if one has to choose, then one requires only 4 bits to send them. So, now just imagine this, that you have a matrix where you have 2 columns only. So, that means, and if there are 4 antennas, so you are basically taking 2 vectors which take 2 data inputs and send them out over 4 such antennas. So, when you write down the expression, you have S1, S2 as a vector multiplied by these W11, W21 up to W41 and W12, W22 up to W42, and this goes into the channel. So, that is how the processing is done, and how one chooses this particular weight matrix is a proprietary mechanism by which one can do it. So, in this way one can take advantage of exploiting the different MIMO spatial data pipes. That means, one would take advantage of the data pipes and one can expand the spectral efficiency. So, in these 2 figures we see the result of the case when channel is unknown to the transmitter and when channel is known to the transmitter for the situation of MT equals to MR equals to 4. So, as your number of antennas increase, you get a different kind of result, but what we see over here is for low SNR conditions, there is a gap in the channel known to the transmitter compared to the channel known, but for high SNR condition there is not much difference between this. So, high SNR condition means that ES upon MT N naught is very high. So, if that is very high, 1 upon ES by MT N naught, this whole thing is very low, which means mu minus this is very high, and there is not much difference between each of the modes that we are going to use. And as your SNR increases, there is not much gain that one would get if one uses full CSI at the transmitter. So, this is something to be remembered. We also talk about the 10% outage capacity. So, there we see that the difference is much more notable, but I mean depending upon the situation, one has to choose the appropriate mode of operation. So, when we use the code book, it is not a full CSI, but a partial CSI information about the channel. The next important thing that we would like to see is the effect of spatial fading correlation. We had seen such a thing for the diversity performance, we will now see it for the capacity results. So, H can be expressed in this form, we have discussed this thing earlier, and we assume MR equals to MT equals to M, and then what we see is that the H Hermitian that we had over here, remember we had H Hermitian. So, if you expand H, it is R half H W R T half, right, and if you look at this, that will be R T half H W Hermitian R half Hermitian, right. So, R T half Hermitian would give to R T, that is what you have, and then you have H W Hermitian, rest of the terms you can easily figure out into this expression. At high SNR conditions, that means when rho is very large, this can be represented in this manner with a log determinant, because we are neglecting the effect of I 1 over here in the diagonal elements, because this is very large, and you have RR and RT through determinant identities. You can just swap these things and you get this RT over here, sorry, RT is over here, and RR half Hermitian would come there. So, what you see is that the capacity can be approximated to the capacity of the spatially wide channel, but there are these additional terms of log determinant of RR and log determinant of RT. This would mean that RR and RT would affect the capacity in a similar manner. If you look at it, their effect is similar. So, we study one of them. Like before, we have to put this constraint that sum of lambda I of R is equal to M. Using arithmetic geometric mean inequality, which we had seen earlier, for the diversity case, what we get is this result. This was also seen earlier. So, now if the determinant of RR is less than 1, log determinant, so let us clear off everything. This entire thing is less than or equal to 1, that means this thing is only less than 0. Similarly, if this is also less than or equal to 1, if determinant, that means this would be less than or equal to 0. Now, when these are identity, in that case the determinant would turn out to be 1, and in that case the log of determinant would be 0, and we will be left with the capacity of a HW channel, which is true when RT or RR equals to 1 identity. When they are not so, since log determinant of them are negative, we see that the capacity drops in case of spatial fading correlation. So, what we see over here is that for a particular configuration that we are showing the results, we find that the spatial correlation has a detrimental effect on the capacity. So, the capacity falls significantly, 3.3 bits per second per hertz. If you just have 3.3 bits per second per hertz, now you multiply, let us say 20 megahertz, right. So, you can get almost 66 megabits per second loss in this particular situation, right. So, what we see is that correlation increases the probability of error and decreases capacity. So, net effect uncorrelated channel gives you much better performance than a correlated channel. So, correlation is only affecting us detrimentally. If we know the details, then we can take advantage of designing the transmission mechanism schemes, which can provide us with a higher spectral efficiency. So, last thing that I would like to show you before we conclude in a minute from now, the capacity of spatially wide channel for large M. This is a motivation for studying massive MIMO. So, what we see is that if you let MT equals to MR equals to M, again for simplicity, and also we let RSS equals to identity of size M, using the strong law of large numbers, as M tends to infinity, you can get this thing. If you open up these things, you are going to get H11, H21, this whole matrix, and H Hermitian would be H11, H21 and so on Hermitian. So, when you multiply these matrices, you are going to get diagonal terms which contain the product of the streams, and the off diagonal would be the cross terms. If it is spatially wide with large size of M, each of the diagonal entries would turn out to be almost same as expected value of H I mod squared, and hence this matrix would turn out to be a identity matrix. This particular part you can check as an assignment for yourself. So, now if you look at the capacity expression, we have H Hermitian with MT below, and RSS has been assumed to be set as identity. So, now what we see is that inside you have H Hermitian by MT, H Hermitian upon MT, we said you are going to get it as IMT, which you can check out doing the derivation for yourself, and it is not a very difficult, it is a few steps and you can get it very easily using the central limit theorem or law of large numbers. Sorry, you are going to use the law of large numbers, you are going to get that, and then with this IMT. So, inside what do we have? IMR plus ES by N naught plus, of course, we are talking about M, we are talking about M, this thing, determinant and a log. So, this is an entire diagonal matrix, and if you see each of the entries are 1 plus ES by N naught. So, this is the SNR of an AWGN or of a CISO link, one could say, right, and of course, one is going to get the one is going to get, if you have made this assumption, there is no other problem, you are only left with ES by N naught. So, this expression is the capacity or the spectral efficiency of a CISO link, that is what we get from here. And now, since we are talking about determinant, so we basically have the product of these things, because that is a diagonal matrix, determinant is a product of these things 1 to M, and you have a log. So, this would be summation of log 1 plus ES by N naught. Since this is a constant term I equals to 1 to M, you are going to get summation I equals 1 to M multiplied by inside of course 1 log 1 plus rho. So, this would result in M multiplied by log 1 plus rho, and that is what you have. So, what you get finally is M times the capacity of a CISO link. This is the biggest motivation, one of the biggest motivation for going towards massive MIMO. That means, as you keep increasing the number of antennas, one would, for an HW channel, of course, we are talking about the HW channel, one would tend towards a situation that you have CISO links and you are getting M times the capacity without any increase in transmit power. So, transmit power remains the same as CISO, but you have an M factor increase. So, all the spectral efficiency that we require can be simply got by linear scaling of the CISO capacity with simply large number of antennas. So, this means as M tends to infinity, the channel becomes deterministic, we will discuss that simply because of this identity operation, and it increases linearly with M, which in other words mean that for every 3 dB increase in SNR, capacity increases by M bits per second per hertz instead of logarithmic increase. So, this is a huge impetus in providing huge amount of spectral efficiency requirements for all future techniques, and hence in the 5th generation system, massive MIMO is one of the major communication techniques which we will briefly overlook in the next lecture along with some more advanced mechanisms. Thank you.